So we welcome you, Itamar, to go ahead with your talk.
Thank you very much. Yeah, it's such a nice program. I really am so sorry I am not able to attend in person. I was really bummed when I needed to cancel my flight a few days ago. But it's an honor to participate at least virtually. And so today, this talk to end the week will be slightly different. Okay, so one difference is on subject. I'll be talking about lattice defects in quantum magnets, topological systems, including topological order. Okay, so it's maybe a little related to the idea of using decoherence to try to generate new behavior. But here, instead of decoherence, it's a quenched disorder, in particular lattice defects. Okay, we'll ask what we gain from lattice defects, but also the kind of approach will be different. So it'll be like a few ingredients on what's possible rather than a kind of classification. So let me say what I mean by that. And I should thank the people in my group who really did the work. Especially, I'll talk about three little tastes of different things. My postdoc, Arnab Seth, was the leader of all three things I'll talk about today. Actually, also, he prepared some of the slides that I'll be using. And other work is by Richie Shu and Faye Burhani. Okay, so the three things, they will be about starting from really related to what we just heard about before adding decoherence, like a Tori code model, where we'll add defects and go from the abelian Tori code to the non-abelian chiral spin liquid to defects. I'll do a little brief foray into an experimental collaboration, just showing how defects can be really visible. And then we'll talk about not topological order, but other kinds of topology, really Chern number that has some surprises, surprisingly, with impurities. Okay, and so the idea here is to look at when we have these interesting different phases that are not just the usual symmetry breaking, maybe one-form symmetry or other kinds of topology. How do these interplay with the lattice? Okay, and so what I'm doing again here is not a classification. I'm not going to give you like a theoretical structure. Instead, I'm going to try to give proof of concept for a few different features. Okay, so these are going to be three little bites. Three appetizers of different features. You can think of them as ingredients, okay, that then in the future you can use these ingredients as fillings in some theoretical structures in the future. However you want to fill your dosa. Okay, so these are ingredients for future theoretical structures. And so just to make sure we're on the same page about what we need for this, I'll be using the honeycomb lattice a lot. And what I need with that is really just to get Dirac cones. Okay, I need to, because I want to connect to particular models to show the proof of principle, I need to be able to connect to concrete models. But what I'll need is the Dirac cones. That'll be just the avenue for topology. What do I mean by that? By adding a mass term, an appropriate mass term in some kind of chirality, time reversal breaking, then we can get a non-zero Chern number, and that Chern number in momentum space comes with chiral edge modes in real space. Okay, so that's like the quantum Hall effect. And also when we have intrinsic topological order together with this topology, then that gets upgraded. We know from Reed and Green the odd Chern number like P plus IP is how I get non-abelian topological order. Okay, so that will be important. And let me actually pause. I want to make sure if people want to ask questions to interrupt, please feel free. Okay, and so the first bite, this first morsel is talking about the Kitaev honeycomb abelian spin liquid, and we'll add defects and get the non-abelian chiral spin liquids. Okay, and so just let me introduce what we mean by this, and also to, as I was saying, to get the chirality, sounds like we should start with some Dirac cones. So how do we get the Dirac cones? From this honeycomb lattice, we have a spin model on the honeycomb lattice, but by having an emergent gauge theory, we can get the Dirac cones. Okay, so the story here you're familiar with. It's the spin liquid, Basker and Anderson. We get ground states that are fully entangled. And so what we end up here is the Tori code. And in this particular model, it's not just the gapped Tori code. On top of the gapped Tori code, there's also a gapless Dirac cone of the Majorana fermions. Okay, so the fermions, that epsilon or F particle that we know from the Tori code, here gets upgraded to a gapless Dirac cone. But otherwise, it's just the same Tori code we've been hearing about. Okay, but that Dirac cone is nice because that Dirac cone is a mechanism for getting chirality. So now let's see how that works out. The other ingredient that was known already from Kitaev's paper is that this model has an interesting feature. The honeycomb lattice is hexagons. But if instead of hexagons, there's triangles like on the left or some kind of random graph like on the right, studied recently by a few papers, then any of these odd-sided plaquettes have imaginary pi over 2 fluxes. So if the M anion is a pi flux, these are plus or minus pi over 2 fluxes. Okay, they're a different quasi-particle. Actually, some materials on the honeycomb lattice are hoped to realize something near the Kitaev spin liquid. And so we could try to hope to get these features there. But if we want to get these odd-sided plaquettes, these random graphs or these other lattices, these are not directly applicable to the Kitaev honeycomb materials because actually there's another geometry ingredient needed to get these XYZ couplings in a real solid-state material. Okay, so what can you do to work with the geometry? How can we get these odd-sided plaquette defects? Let's break it down. Let's start with the basic odd-sided plaquette defect, which is a disclination. Away from the 6-sided hexagon, it could be 5 or 7-sided. But if I have a disclination, that adds curvature that definitely spoils all the geometry. Okay, I can bind 2 disclinations with opposite charges into a dislocation. Pictured here, I'm using these pictures to show visually so you can see the tail of the dislocation. In reality, of course, it would have some elastic relaxation. Dislocations were studied a decade ago in the gapped phase, but to realize them geometrically, again, is an issue. They require this string of flipped Kitaev colors. So locally, they're okay, but actually, if you zoom out, they cannot be okay, even in principle, in a solid state realization. So if we want a solid state realization, Arnab pointed out, and then we were able to proceed with what I'll be showing you. You can actually bind 2 dislocations into what turns out to be a defect that does exist in honeycomb lattice materials like graphene. It's called the stone whales defect. Okay, so now we can study these stone whale defects, and already we can see the geometry considerations do work out. So I'm showing some picture here. It's a little tough to see from the picture because it involves some out-of-plane movement, but this is a realizable defect in the geometrical considerations of the Jekeli-Kalulin mechanism, which I'm not going to get into, but basically you can really realize this. Okay, there is a reason to study this, even as a toy model for realizable Kitaev spin liquids. And then there will be other local effects, but as always with topological order, it's robust to any perturbation. So if perturbations are small enough, I can ignore them. Okay, so one thing we studied, the first thing to look at is what are the ground states? And it turns out, indeed, there's different ground states, and there's a bunch of odd-sided plaquettes involved in this defect. But it turns out that the two ground states, the time reversal pair, are exactly the states with a large net chirality. So here we're showing some measure of local chirality. It's an adaptation of the local churn marker that we've adapted to work with the background gapless Dirac cones. And you can see one of the ground state here shown on the left that has a large net topological magnetization. That's what's being shown here. While an excitation, here it's like one of the flux excitation would have no net chirality. It's like a dipole. Okay, so that's good. That's really an important thing. That means these defects carry a net chirality, which would not have been obvious. And we can measure this net chirality in different ways. On the left is that local churn marker, which is topological magnetization of the emergent Majorana fermions. On the right is the microscopic scalar spin chirality of the spin 1/2s. And they show different microscopic behavior, but the pattern is the same. Okay, and also both of these are actually measurable as real electronic magnetization coming out of this topological orbital magnetization of the fermions. So these are observable, and we can also understand all this using the impurity T matrix. Arnab's computation was able to show, well, first order, we can see there's terms that try to open a trivial gap and a term that opens a non-trivial topological gap, and that's the term we want, and it comes with an extra factor of √3. That √3 allows it to win and allows us to get the churn number out of gapping out the Dirac cone. And then you might worry if you actually do a full resummation to all orders of perturbation theory, will that change? But it turns out the √3 gets even larger enhanced. So we really do get a churn number. That's what we hope to get. And so this tells us if we had a bunch of these defects, and they all had the same flux, like plus pi/2 flux, then we would get a churn number that would give us the non-abelian spin liquid. So the one last ingredient we need is to ask, if I have a bunch of these defects, they each come with this Ising degree of freedom. This defect chirality is large, but can have either sign, plus or minus. So that gives us an effective classical Ising model, a statmic model, that then we study. In studying this model, we can compute the emergent interaction by looking at the difference between aligned and anti-aligned configurations of defects. There's a few other things we do. They all give the same answer. Okay, so here is the plot. Here you see this is a log-log plot of that energy difference between aligned and anti-aligned defects. And it's a straight line on a log-log plot. So we know what that means. That's a power law interaction, the straight line on a log-log plot. And it's a quite long-range power law. Okay, so the emergent interaction between these pi/2 fluxes on two defects that are far away from each other, those chiralities, the pi/2 fluxes, the chiralities associated with the various pi/2 fluxes on each of the plaquettes have this power law. This power law is ferromagnetic, so they prefer to align, and it's so long range that it's actually very easy for them to align. Okay, it's actually even if you take some idealized Dirac cone and do the field theory computation, you would get a shorter range power law, r⁻⁻3, but because of the finite defect density, it gets renormalized, and it turns out it gets renormalized to something even longer range. And that very long-range ferromagnetic interaction then gives us the chiral spin liquid. Okay, in particular, there is now a finite temperature transition, which usually for a 2D topological order, there's never any finite temperature phase transition. But here, because we need to have spontaneous symmetry breaking associated with different chiralities, we get it. Yes, was there a question?
Is there a easier approximate understanding of why this gamma is normalized downward, less than 3?
Yeah, that's a great question. Actually, we only have a partial understanding. That the partial understanding is kind of mathematical. If I try to imagine cutting off, I can work with like the spin local density of states from the Dirac cone and you do some integrals to get this. This is like an effective RKK. It's kind of RKKY interaction. It's not. There's no oscillations, but it's related. Okay, and then if I cut off these integrals by a finite density of defects, that's consistent with gamma being renormalized down to give you longer range interactions.
I see.
So this is the best understanding we have right now. But it's quite surprising, actually. Yeah, it's very, and that's very powerful. And actually, then it turns out we can look at some kinds of perturbations. Some kind of perturbations preserve the exact solvability, so we can study them, meaning families of stone Wales defects that are somewhat different from each other. And for some perturbations, these perturbations can change gamma. Some of them can change this effective gamma even more. Okay, it's an effective gamma over some length scales up to the defect density, but that's the relevant length scales for generating this instability. Once you get the instability, everything gets cut off. This finite temperature instability. But basically, this gamma can get suppressed. So the gamma is 2.7 for the kind of conventional stone Wales defects, but we find we can suppress it down to 2.3. And if you push it down to 2, then TC diverges as 1 over gamma minus 2. And then it's cut off by some other flux scales. So it's pretty cool. You really can get this high temperature phase transition. And again, it's the transition into the chiral spin liquid because we found we have churn number 1. That's like the same mathematics as P plus IP superconductors with the Majorana zero mode giving non-abelian statistics. Good. Any other questions on this? This is the first taste of what's possible. These local lattice defects interplay with a topological order to get upgraded to this long-range interaction and non-abelian chiral spin liquid instability. Okay, so now let me have just a very quick kind of foray into relating to experiments. I think that's always helpful to just keep in mind, well, what are we why are we doing what we're doing? And this was a nice collaboration with experimentalists at Georgia Tech that really shows how defects can make a difference even if they occur at very low density. Okay, so now for this little bit, I'm going to do away with generalized symmetries. I'm just going to have trivial symmetries here, just a classical spin order, this up-up-down magnetic order. Usually you would think defects don't do much for these classical states, actually. But in this case, we find they will. And it was a nice puzzle. This is another way of doing physics. We stare at this experimental data and try to help the experimentalists interpret it. Okay, and first we don't need to assume this order. We say, how far can we interpret it without this order? There's a bunch of spectral lines here. The main line is clearly just spin wave excitations. But then there's other lines. You can even see by doing exact diagonalization on small system sizes, these are multiple spin flip excitations. There's the bottom of the continuum of multiple spin flip excitations. Okay, so that captures some of these lines, but actually the lines captured by the triple spin flips are the weaker ones. The weaker one. The secondary lines, the 3 secondary lines are missing here. And in hindsight, the answer may be obvious, but actually it took us a long time to figure it out. And though I do disorder, it was Arnab who pointed out disorder can fix this. If we assume that some bonds are weaker than other bonds, that modifies the energy of some spin flips in a particular way that then when we exactly include these bonds, we exactly capture these three lines. And there's a relation between how these lines are shifted. The secondary disorder lines are shifted relative to the main lines. And so these relations constrain the parameters, but everything exactly fits. Okay, so even with the constrained parameters, this exactly works. And in particular, we can, one of the parameters in this simple model is how much is the reduction of the weak bonds. And we find these weak bonds are reduced by almost 100%, which means they're basically broken bonds. Some atoms are missing in the crystal. That really makes sense, and that was nice. We gave a model that had an extra free parameter, and we found that parameter naturally was tuned to 0 with a natural physical interpretation. And then there's other numerics that can be done just to confirm with this disorder and triple spin flips, everything is captured, and these sharp lines are the fingerprint of the disorder, even at this low density. Okay, so that's another manifestation. Even a dilute density of defects can really be visible in experiments. Yeah, any questions on this little bit of the second part?
The fact that the lines remain sharp, is it evidence that the perturbation induced by a defect is very local? But how does it fit with the previous picture? You said that you have very long range interactions between defect, or maybe that has nothing to do with the previous part. Or...
Yeah, exactly. Thank you. Good point. So exactly. So here, the sharpness of the lines is exactly the locality of the interactions. And that has to do with being in this UUD magnetization plateau. Okay, the UUD magnetization plateau is enabling the locality. It's really because it's stabilized by interactions that are relatively classical, like mostly Ising. And so indeed, in these three different pieces are kind of unrelated. So these defects have no relation to the first story. Here, this is this kind of semi-classical picture. These are two different ways where even dilute defects can have a big effect. Yeah, the first case was I needed to start with a billion Kitaev spin liquid, and then the dilute defect had the effect of giving the chiral spin liquid. Here, I don't need to start with a spin liquid. I start with this classical state. I don't get anything long range. Everything is local, but still things are visible. Actually, they're visible in these sharp lines.
And do you think there might be a prospect to see rare clusters of defects that could give additional lines, or is it totally ruled out?
Yeah, that's right. So surely there's many other lines that should be visible with a reduced weight. And I should say, so some of these lines, including the disorder lines, they're really the top or the bottom of continuums. Okay, and it's that large density of state at the edge of the band of excitations that becomes visible as the sharp line. What allows it to be sharp here is the UUD phase, so that it's mostly semi-classical, like mostly Ising interactions. That's what makes it especially sharp. But that's right, there would be actually first a continuum and then also other lines from clusters of defects. Exactly. Good. Any other questions on this part? So my goal with this, like a 3-ingredient whirlwind tour, is to say is a kind of it's not mathematical structures. I also don't have time we have some of that, but I don't have time to present it. But I just wanted to give you a taste of what's possible as a motivation for understanding some broader structures. And so the last thing I want to talk about is another effect that you can get from disorder, where again, the disorder here is local defects at small density, so they're dilute. Okay, we know, again, we know that in principle, disorder can give weak symmetry breaking, can give new kinds of phases. And here I want to show how in really looking at some concrete microscopic model, seeing how the disorder can have quite surprising effects. Okay, and so in this case, it's not a new kind of phase that we'll get, but a new effect of disorder. So the IR theory is a known IR theory of some Chern number topology. But the way to get from the UV to the IR is going to be different here. That's the story here. It's the approach from the UV to the IR. Okay, so what is going on here in this last story? Again, the honeycomb lattice, so that we have Dirac fermions. And now we're going to talk about magnetic impurities. Okay, so the context should be the Haldane honeycomb model, which I showed here on the left, where if I can break time reversal everywhere on the lattice by having this pattern of imaginary second neighbor hopping, that's the blue lines. These blue lines with arrows are imaginary hoppings. They give a flux pattern, zero net flux, but there are fluxes giving these imaginary hoppings. And this model is the model for the Chern insulator, quantum Hall effect on the lattice. It opens the gap in the Dirac cone and gives a Chern number. Okay, but now we can ask, what if we put these imaginary hoppings on just one hexagon? It's kind of related to the Stone-Wells defects, like something on just locally, some local defect. Here, this local defect is like a local magnetic impurity, but instead of being spin, there's no spin here. Instead of being spin, it's an angle, it's an orbital magnetization, or like orbital angular momentum magnetic impurity. And then we can ask, what do these isolated magnetic impurities do? Do they do the same thing that the Haldane honeycomb model does? So also, while we were studying this, this recent paper came out from Pullman and Nolle just a few months ago that points out, indeed, not necessarily having these dilute impurities can give another phase. And so this is a phase diagram for randomly placed finite density of defects. And you can see usually if I have a lot of these defects, large impurity density at the top of the phase diagram, I get a Chern number 1 phase. But for small density and larger impurity strength, there's a transition into the Chern number -1 phase. And that transition is a chirality reversal. It's a reversal of the Chern number from 1 to -1. Okay, and it's a very surprising transition. It comes, it's the tricritical point with a thermal metal. And so there's actually some mysteries to understand about this phase transition. And so to complement this, how do we understand what's going on here, in addition to just seeing this numerical observation? There's the change in Chern number can also be understood by projecting a T matrix to a Dirac cone. But to understand this, why this occurs in the dilute impurity limit, Arnab again suggested, we study a single defect. Okay, and so that's what we proceeded to study. That limit of low impurity density would be just a single defect. Would that still be enough to show this physics? And then can we use this simpler limit to actually understand what's going on? So first we need to ask, is it enough to show this physics? And we find it can. Okay, so we put this defect even in some finite system so that we can look at all the low energy currents circulating around this defect. Again, these low energy currents are like what would be the chiral edge modes. Here, the chiral edge modes are not as well defined because we start with a system that's almost gapless. How do you define anything when you have almost gapless systems? All the classifications of topology that we're familiar with, bulk boundary correspondence, require a gap. Okay, so how do we do this? Still, we don't have to identify the edge mode. We just look at all the low energy currents circulating around the defect. Whether you call them edge modes or not, up to you, but these are all the low energy circulating currents, and they do show this clear transition with almost no finite size effects. We see that they're positive for small defect strength h, and then they all cross at some critical defect strength and become negative. And you can really see this looking at the currents. Okay, similar to currents, we can look at the orbital magnetization. Here it's the topological orbital magnetization.
Can I ask a question?
Yes.
The single particle spectrum, do you have bound states in the gap? And if yes, how do you set up the Fermi energy? Because I guess it corresponds to a field Fermi seed, those patterns, no?
Yeah, exactly. Okay, so setting the Fermi energy is easy because we here are keeping particle hole symmetry to make this simpler. So Fermi energy is fixed at 0 at the half filling of the Dirac cone. And before we add the defect, there is no gap. Once we add the defect, it opens a local gap, but away from the defect, there is still no local gap. And then you are right that there is still a notion of a bound state of the defect, and that's exactly the explanation. And I'll get to that in the next slide. Does that answer the question?
Itamar, could I also ask a question? This is Andrei Nevedomsky.
Yes.
So what determines the chirality? So chirality usually means that the product of time reversal and inversion needs to be preserved. Here you have disorder, so obviously no inversion symmetry. So what determines which way, left or right, the impurity induces the currents?
Yeah, exactly. So here by chirality, I mean circulating currents. Okay, they're circulating counterclockwise around the impurity. So let me say it like this. But then also to answer your question about one of the virtues of looking at a single defect is that we can keep the inversion symmetry, and we do. We keep inversion around the middle of that hexagon. Okay, so we have inversion. And then we can really see the effects. Yeah, so we add this orbital magnetization impurity. It breaks time reversal. In a particular sign, okay, we add this up impurity. It's an impurity with orbital magnetization pointing up. And then the response, indeed, as we add this impurity perturbatively, the response is the fermions circulating around it to give more orbital magnetization pointing up. We add the impurity pointing up, we get a response, orbital magnetization pointing up. Orbital magnetization pointing up means counterclockwise currents, but we can measure either one. Low energy, edge currents, or bulk orbital magnetization. And the shocking thing here is that as we add this up impurity and we make it even stronger up magnetization, at a critical value of the strength of the up impurity, the response flips sign. The response of the Dirac cone flips sign, and suddenly above this critical impurity strength flips to down orbital magnetization with clockwise circulating currents circulating around the impurity.
And do you have an intuitive explanation for why? So some non-linear magnetization induced by this impurity?
Yeah, exactly. That's right. Yeah, and I'll get to that later. Right. So indeed, first of all, like a necessary ingredient here is a non-linearity of the magnetization, and we find it growing. You can see in the orbital magnetization, there is some. We find that magnetization growing as you approach this transition. And then the way we understand this transition is by looking at the bound states and the T matrix. Okay, so then Noller work, which computed hole conductivity for the randomly placed finite defect density, also shows that in taking the T matrix and projecting to the Dirac cones, there is a resonance associated with this. Okay, so now we're trying to understand, can we understand this resonance in real space? So looking at this local defect first gives us this resonance visibly in the orbital magnetization in the current. You can really see that these curves of orbital magnetization or currents look like a resonance because they go up almost like they're trying to go to plus infinity and then jump from plus infinity to minus infinity. And change sign from plus to minus by going through infinity. That's the signature of a resonance. Okay, so now let me tell you how we interpret this resonance. Before I go, let me start with the most basic thing. Okay, that the master student that Arnab mentored here and Arnab figured out this 6 site. If I just look at the 6 sites of the single hexagon, okay, that's as local as you can get. Certainly, there's no phase transition in a system with 6 sites, but still, there's a hint of the phase transition that you end up getting, because we can look at there's 6 different states. 2 of them come as low energy states. Okay, it turns out to be the 2 states with angular momentum of the bottom row of this table. And these have a current that changes sign at some value. That's a local change of sign of the current. It's not a phase transition. But this local change of sign of the current, then when Arnab computes the impurity projected T matrix in real space, that impurity projected T matrix shows a resonance. Okay, and the resonance occurs from exactly the same 2 impurity bound states as what you get from just this 6-site toy model. What do I mean by the same 2 states? It's literally on the 6 sites, it's the same 2 states with the same angular momentum. And then the Green's function is just what brings these bound states into the quasi-localized behavior away from the defect. Away from the defect, again, things are gapless, but these are still quasi-localized bound states. And so we can see this resonance. The resonance gives a transition, and we really see how it comes out of this local physics locally within the defect. Okay, so the position of the resonance is the same as what Polman and all, Niels Polman and all see from the Dirac cone projected T matrix. Here we're seeing it in real space. We're able to see the same resonance. We see that it comes from these 2 particular bound states. We see it's the same 2 bound states that you get just by looking at the 6-site toy model. And then we also see what ingredients of the Green's function give the position of this resonance, and it turns out it's the 3rd neighbor term of the Green's function that takes you from the HC prime of the 6-site case to the HC, the true phase transition of the full system. And the single defect is enough to understand this chirality reversal phase transition from these bound states. Yeah, does that answer the question, or any other questions on this? And this is a good time to end. So this is the conclusion. Okay, so these are, we're looking at lattice defects in quantum magnets and topological systems and asking, okay, thanks to looking at these ingredients of topology, what can the defects do? And we saw you can get the chiral, the non-abelian spin liquids, defects can be visible in experiments, and then this global topology coming from the local impurities, that local bound states generating this global topological phase transition of the Chern number flip 1 to -1. I say Chern number, but I can also see it in topological orbital magnetizations, the edge mode of the low energy current, circulating currents, etc. Okay, and so these are not mathematical classification structures, but I hope they serve as proofs of concepts. And then the question for the future is what structures could be generated by including these ingredients. Thanks.
Thank you very much, Itamar, for this very exciting talk, and we are open to questions now. Yeah, please.
Itamar, this is Andrei again. So to the first part of the talk, so see if I can follow through the argument. When you have the odd side number rings, you have this flux, Kitai flux, that's plus or minus pi/2, if you will. But
Yes.
the sign is what? Is it determined randomly, or what determines the sign? So
Yeah,
let me ask the question. Generically, what I'm wondering is when you create the stone Wales defects,
Yes.
What determines the sign of chirality?
Yeah, good. So it's two levels to this question. For a single odd-sided plaquette, like a disclination, it's ground state degeneracy. It's twofold degeneracy. Time reversal protected degeneracy. Then when I couple these defects, putting them together into a Stone-Wells defects, which is a bound state, a quadruple of 4 disclinations, they couple in a complicated way. And actually, we have some understanding of why it turns out it should be this case. They end up coupling, quote unquote, ferromagnetically in terms of the defect chiralities, not in terms of fluxes. In terms of defect chiralities, we have a formula that relates the chirality to the flux. Okay, so it turns out the flux on a 5-sided plaquette generates opposite chirality relative to the same flux on a 7-sided plaquette. But what is the emergent interaction, even at the source scale, is ferromagnetic, so that's why we end up with a Stone-Wells having still just a bunch of flux states, but 2 of them are ground states, and they're exactly the 2 with large plus and large minus net chirality. And for a single defect, they're degenerate, so that gives the classical stat-mech Ising model of no magnetization, no magnetic field in this Ising model, just degenerate Ising spins that now have emergent coupling between them to give a spontaneous symmetry breaking transition.
But okay, so first of all, thank you. I understand better now. In order to get to the chiral quantum spin liquid regime, though, you have to somehow globally break the time reversal, right? Do you form domains generically, or did you start with, let's say, up-polarized state for the sake of the argument, and that's why you got the state that you got?
Yeah, exactly. To get the chiral spin liquid, we need the spontaneous symmetry breaking of time reversal to generate this order parameter, scalar spin chirality or local churn marker, etc. And that spontaneous symmetry breaking, that's a classical question. That's the classical question answered by looking at the Ising model. We compute the emergent interaction that feeds into the Ising model, which is this ferromagnetic power law long-range interaction. That's what is mediated by the Majorana fermions. But once we have it, it's just a question of the Ising model, and this ferromagnetic random site Ising model has the spontaneous symmetry breaking phase transition. We don't assume it, we show it.
Gotcha. Thanks.
Yeah. Actually, the transition, by the way, that transition is almost a mean field. It's really a mean field transition, it turns out, because it's such a long-range interaction. So it's as simple as you can get for an Ising model transition.
Are there any further questions? We don't see any more. So thanks again, Itamar, for the very exciting talk. And we hope we would come here again at some point. Yeah.
I would very much like that. I really am bummed to not be attending in person. Yeah, it's such a nice workshop. So yeah, I hope this was a nice talk for the end of the week.
Yeah, that's indeed true. And have a nice weekend. Thanks.
Thank you.